Yeah, I tell you about the data we used. What we wanted to do is an analysis of the feed-in of PV and wind power. So what we needed were data to simulate this. And these are the data we used. We used for the wind power, or for wind speeds, the WASASSODA, which was presented by Andre earlier. And we got temperatures as well. And we got a grid about 5 times 5 kilometers about all of South Africa. And it was time series with 15-minute steps from 2009 to 2013. We got also different height levels from 50 meters to 150 meters because we wanted to simulate different turbine types which have different heights. For PV, we used the SODA data, irradiation in a resolution of 0.2 degrees. Also 15 minutes, but only from 2010 to 2012. And at a height of 2 meters. And also we used the WASA temperature data for the PV simulation. The wind speeds, this is an example how they are distributed about South Africa. These are mean wind speeds from 2009 to 2013 at 100 meters height. And you see in South Africa, you have higher wind speeds, and going into the country, they get a bit lower, and here are some places with much lower wind speeds. So, depending on this, we decided which turbines we place where. Still, we only got a 5 times 5 kilometers grid, and we wondered if this is enough, the resolution. And to check this, we couldn't get smaller resolution, so we did the other direction and looked for a higher resolution and how the changes are. So we had, in the first step, we considered every pixel, and then we imitated a larger grid by taking only every second pixel and every third pixel. To be sure that we don't make a mistake, we also did different start pixel. This is especially relevant in the wider distances, because if you start at that pixel or at the next one, you only have 350 kilometers distance. And so we got different layouts for every resolution and compared the normalized standard deviation of the whole wind power feed-in of South Africa. And what you can see here is that until about 100 kilometers distance, we have a quite stable behavior. And also, we looked at the standard deviations of the ramps for 15 minutes gradients. And also here, we see that from 5 to about 20 kilometers resolution, there is a quite stable behavior. So, what we say is that 5 kilometers should be sufficient for such a study, which is nationwide. For the demand, we also got the data from 2010 to 2012, historical data for the entire country with a temporal resolution of 30 minutes. And we have an annual demand of about 225 terawatt hours and assumed a future demand of 500 terawatt hours. So we scaled the demand time series that we have and allocated to the grid nodes. What we did, we have the weather data from the weather models. Then we generated wind and PV time series from this and have the potential electricity generation. We distributed wind and PV all over the country in different scenarios. First, we did the time series for each pixel that we have, and then we defined different scenarios and distributed the wind resource and the PV resource. And then we aggregated the time series again for the whole country. On the other hand, we have these demands time series, which we prepared for future electricity demand. Altogether, we could get the residual load time series for each scenario and get the results of the study. The wind turbines that we used were different for independence for the wind speeds and the pixels. So there are wind turbines which are smaller for sites where are higher wind speeds, and where the wind speeds are lower, they might be higher in a higher level. So you would install a higher height of wind turbines. Depending on these wind speeds, we chose for every pixel which turbine would be there. And this you can see on this plot. So all the yellow sides, there is still the turbine with the number 1. So here we have high wind speeds, and going up to the turbine number 5, which is this for the lowest wind speeds, which is in most bases of South Africa used. What you can see here are the power curves of the 3 different turbine types, and you see that the turbine for the higher wind speeds starts at higher wind speeds going up, and those turbines for the lower wind speed reaches its height level already at smaller wind speed. Still, we have only this 5 times 5 square kilometers, and not every turbine will have the same power at the same time. So we smooth the power curves, and these are the power curves that we used finally. And yeah, further on we did have exclusion areas that we couldn't use because there were already buildings or streets or water or something, and we excluded them from all from the other spaces. So finally, I want to explain residual load because that's quite important for the whole study. What we have in the first is the demand of the country, and then we want to know how much has to be given by this conventional energy or flexible energy if we include unflexible power sources. So we have the demand here, and then this is given by PV, and this is given by wind. So only what's left would be this brown. area, and this has to be, well, flexible power plants have to feed in here. And here we have the minimum. There we might have to curtail the wind turbines. So also we see the maximum of the residual load is going down, and we don't have to feed in such so much gas or coal or something like that. But what's important as well are the gradients, because you need a power plant who can react on the gradients that are produced by PV and by wind. That's why we also often look at the gradients in the slide.
Now that you already heard a lot of things about the data we use and the methods we apply, I want to introduce the scenarios to you. The scenarios were developed to investigate different spatial distributions of wind power in the country. And first of all, I will show you. First of all, I wanted to look on the left side. On the left side, we show some penetrations of PV power in the system. We had a fixed scenario for solar PV because the study focuses on the aggregation effects of wind. This fixed scenario was scaled to 40 terawatt hours, 80 and 200 of electricity generated from solar energy. And then on the right, we have the same done for wind. We have different steps of wind penetration of 50 terawatt hours, 100 and 250. But then we also have about, it depends a bit on how you count, but we have 9 different scenarios for distributing the wind turbines. And this way we get to investigate all kinds of shares of renewables in the system. So for the first step here, we have not so much PV energy and not so much wind energy, which leads us to about 18% compared to 500 terawatt hours of demand. And in different steps with more PV or more wind, depending on the scenarios, we get to 28 and then, 26, 28%, 36 and so on until we reach 90% of renewables with 200 terawatt hours of PV and 250 terawatt hours of electricity from wind. In the following, I will describe the scenarios in detail. First of all, we have a group which we call scientific scenarios, which means to say that these scenarios are not very likely, but still assessing them will give us important conclusions about how the South African power system would react to different distributions of wind. The first one is the uniform resource distribution, where we assume that the whole country is used for distributing turbines. And then on the opposite, we have a second scenario, which is called all in one place. Here we assume that all the capacity we need can be put into one pixel, so into one of the 25 square kilometers squares. In addition to that, we have a high wind speed resource distribution, where we allocate the turbines to those areas with the highest average wind speeds, and a minimal ramps resource distribution, which is an optimization according to causing minimal ramps of the residual load, which Ann-Kathrin just explained. This one results in selecting pixels that are not always the best ones. So it's not the highest wind speeds, but it's the ones that cause the minimal gradients, which sometimes lead to pixels being used that have, for example, low wind speeds or low load factors. We will see that in the following as well. Then we also have some areas in South Africa that are already designated for the installation of renewables. This would be the EIA areas. EIA stands for Energy Environmental Impact Assessment Area, and the REDs. The REDs are the Renewable Energy Development Zones. So we have a scenario for each of those areas, or these groups of areas, and then we also have a scenario focusing on the overlapping areas. Finally, we have some really grid-oriented scenarios where the distribution is done according to the current grid, so the high voltage grid nodes that you saw before in the picture with the demand. And also we get some data for future grid nodes. So a second grid-oriented scenario would be one where we take into account the current grid nodes plus the future grid nodes that are planned. In this picture you can see, first of all, this red cross here. This is the location of the all-in-one place scenario. It's a pixel that is slightly above average, so it has slightly better conditions than an average pixel in South Africa. And what you can see here as well are all these little dots. These are the grid nodes that I just talked about. The light blue ones being the current grid nodes, the existing ones, and the purple ones being the grid nodes planned for the future. In this graph, you can see how much capacity would be installed for the different scenarios. The uniform resource distribution and the future grid-focused resource distribution being the ones with the lowest installed capacity. For the future grid-focused resource distribution, this might seem a bit surprising. It's not, because what was done here was the allocation of turbines was done according to their distance to the grid nodes. So it was the minimal distance locations were chosen, but there was also a criteria saying that the full load hours had to be more than 3,500, and this way you don't need to install that much capacity if you operate the turbines a lot. For the minimum ramps, on the other hand, as I mentioned before, minimum ramps can be reached not always with the best pixels, but sometimes with the pixels with the worst conditions. So in this case, if you have pixels with less wind speeds, you of course need to install more capacity. For the space requirements, we assumed 0.1 square meters per megawatt installed, which leads us for the scenario with the lowest wind penetration, to an average value of about 1,500 square kilometers, which would be only 0.1% of the South African land mass. For generating 250 terawatt hours on average, we would need only 0.6% of the land mass. This shows how much space you have and how little you would have to use for installing turbines to, for this scenario, get to about the demand you have today, or about half of the demand that we assumed for the future. For the solar PV, we only have one scenario. Here we assume that 70% of the energy is generated from rooftop installations and 30% from ground-mounted PV. The ground-mounted PV is assumed to be installed in the EIAs only for this scenario. So we reach to a potential of 220 gigawatt installed for ground-mounted PV, which would generate about 420 gigawatt hours of electricity per year. For the rooftop installations, which were put into settlement areas, you can see those here, we got to 72 gigawatt installed producing 136 terawatt hours electricity per year. So in total, for PV for this scenario, we could install almost 300 gigawatts and produce 550 terawatt hours per year, which is even more than the assumed future electricity demand. And mind, these ground-mounted PV were installed in EIS only. There would be much more space to put the facilities.